My name is Kavita from Basic Chemistry on our first year. Today I made a video on the chapter thermodynamics. General introduction. It is well known fact that the most of the physical changes and chemical changes are accompanied by the energy changes. These energy changes may take place in the form of heat, light, work, electrical energy, etc. All these forms of energy are convertible into one another and hence are related to each other. Quantitatively, the branch of science which deal with the study of different forms of energy and the quantitative relationship between them is known as the thermodynamics. When we confine our study through chemical changes and chemical substances, only the restricted branch of the thermodynamics is known as chemical thermodynamics. The complete study of thermodynamics is based upon three generations called first, second, and third law of thermodynamics. These laws of thermodynamics apply only when the system is in equilibrium or moves from one equilibrium state to another equilibrium state. These laws have been arrived to purely on the basis of human experiences, and there is no theoretical proof for any of these laws. However, the validity of these laws is supported by the fact that nothing contrary of these laws has been found so far, and nothing contrary is accepted. The importance of thermodynamics lies in the following facts. It is help us to predict whether any given chemical reaction can occur under the given set of conditions. It helps in the predicting the extent of a reaction before the equilibrium is attained. It third is it helps to reduce some important laws like law of chemical equilibrium, distribution law, etc. The limitation of thermodynamics where it fails to give any information are as follows. It helps to predict the feasibility of a process but does not tell anything about the rate at which the process takes place. It deals only with the initial and final state of the system but does not tell anything about the mechanism of the process, the path followed by the process. It deals with the properties like temperature, pressure, etc., and the matter in bulk. Microscopic properties, but does not tell anything about the individual atom and molecules' microscopic properties. The name thermodynamics was given by the mechanical engineers in the beginning who were interested only in the conversion of heat into mechanical work. Thermo means heat and dynamic means motion resulting into the mechanical work. Some basic terms and concepts. Some basic terms and concepts commonly used in thermodynamics are briefly explained below. System and surrounding. The part of the universe chosen for the thermodynamics consideration, the study of effect of temperature pressure is called as the system. The meaning portion of the universe excluding the system is called the surrounding. Thus, the system and the surrounding together consist the universe. Universe is equal to system plus surrounding. However, as the entire universe is not affected by the changes take place in the system, therefore the partial purpose, the region of the space in the neighborhood of the system is known as the surrounding. A system usually consists of a definite amount of one or more substances, and it is separated from the surroundings by a real or imaginary bounding through which matter is energy can flow from one system to the surrounding or vice versa. So types of system: open, closed, and isolated system. Open system: a system is said to be open system if it can changes one both matter and energy into the surrounding. For example, if some water is kept in an open vessel, or if some reaction is allowed to take place in an open vessel between piece of marble and HCl. Actions of both matter and energy take place between the system and the surrounding. Animal and plants are open system from the thermodynamics point of view. B is a closed system. If a system can exchange only energy with the surrounding but not matter, it is called a closed system. For example, if some water is placed in a closed metallic vessel, or if some reaction is allowed to take place in the center enclosed by a piston, figure 6.2b. As the vessel is closed and connecting walls, exchange of energy can take place between the system and the surrounding. If the reaction is exothermic, heat is given to the system to the surrounding. If reaction is endothermic, heat is given by the surrounding to the system. Further, if reaction is accompanied by a degree in volume, mechanical work is done by the surrounding on the system. If the reaction is accompanied by the increase in volume, the mechanical work is done by the system on the surrounding, as mechanical work is a type of Energy. The movement of the piston is an out amount of exchange of energy between the system and the surroundings. Isolated system. If a system can neither exchange matter or nor energy by the surrounding, it is called an isolated system. For example, if water is placed in a vessel which is closed as well as insulated, no exchange of matter or energy can take place between the system and the surrounding. This constitutes an isolated system. Here to see in figure 6.3. The place tea placed in a thermoflask is an example of isolated system, whereas the tea placed in closed steel teapot is an example of closed system, and tea placed in a open cup is an example of open system. State of a system and state variable. The state of a system means the condition of the system which is described in terms of a certain variable measurable properties such as temperature, pressure, volume of the system. If any of these properties of system changes, the system is said to be in different state. The state of the system changes. That is why these properties of the system are called state variables. A process is said to occur when the state of the system changes. The first and the last state of the system are called the initial and the final state respectively. Fourth is the state function. A physical quantity is said to be state function if its value depends upon the state of the system and does not depend upon the path of the which state has been attained. For example, a person standing on the roof of a five-story building has a fixed value of potential energy irrespective of the fact whether he reached there is stairs on by the lift. This potential energy of the person is in a state function. On the other hand, the work done by the legs of the person to reach some height is not a same in the two cases where he went by lift or by stairs. Our work is not a state function. Instead, it is sometimes called a path function. Alternatively, a physical quantity is said to be state function if the change in its value during the process depends only initial state and the final state of the system and does not depend upon the path or a route by which change take place throughout. Example of physical quantities which are state function including pressure, volume, temperature, internal energy, enthalpy, entropy, free energy, etc. as discussed later in the unit. Volume, it is state function because, for example, changes in volume of a water in a pond independent of a route by the water is filled by rain or tube well or by both. Similarly, temperature is a state function because it does not matter how a temperature has been attained by heating or cooling, etc. Also, the change in temperature, say from 25 degrees Celsius to 35 degrees Celsius, depends upon the initial and final temperature, does not depend upon the route taken. Fifth is macroscopic system and microscopic properties, extensive and intensive property. If a system contains a large number of chemical species, atoms, ions, and molecules, is called an macroscopic system. The word macroscopic implies large quantities. Thermodynamics does not deals with the properties of any individual molecules but deals with the matter in bulk. Such properties of the macroscopic systems like temperature, pressure, volume, density, melting point, boiling point are called macroscopic properties and thermodynamic properties. These are the further classified into the two types as follows. Extensive properties. These are the two properties which depends upon the quality of the matter contained in the system. The common example of these properties are masses, volume, and heat capacity. Beside these, some other properties discussed later in the unit, including internal energy, enthalpy, and entropy, gives free energy. The total value of the extensive property is equal to the sum of the values of the separate parts, which the system may be divided into the sake of the convenience. Intensive properties. These are these properties which depends upon the nature of the substances and the independent of the amount of the substance present in the system. The common example of these properties are temperature, pressure, refractive index, viscosity, density, surface tension, specific heat, freezing point, boiling point, EMF of the cell, pH of the solution, mole fraction, molarity, etc. It is because pressure and temperature are intensive properties independent of the quantity of the matter present in the system. They are frequently used as variable and to describe the state of the matter. It is of interest is not extensive properties may be different intensive property by specifying unit amount of substance considered, thus mass and volume and extensive properties, but stand specific volume an intensive property of the substance. Similarly, heat capacity is an extensive property, but specific heat is intensive. Extensive divided by extensive is equal to intensive. Mole fraction mole of the compound by total number of the moles. In fact, any mole property Z is an intensive property because in an extensive property Z for the one mole is the substance is xm is equal to x by n. This becomes independent of the amount, molar volume Vm and molar heat capacity Cm, etc. Temperature Y volume is extensive, but a temperature is intensive property. Consider a closed vessel of a volume V containing a gas at temperature T. If the portion is put exactly in the middle, each part of the volume V by 2, but temperature will remain the same. T is the part. Thermodynamic equilibrium system is said to be the thermodynamic equilibrium if the macroscopic properties like temperature, pressure, etc. do not change with time. Thermodynamic process is said to occur when the system changes from one state to another. The different processes commonly meet within the study of the chemical thermodynamics as follows. First is isothermal process. When a process is carried out in such a manner that the temperature remains constant throughout the process, it is called an isothermal process. Obviously, when such a process occurs, heat can flow from the system to the surrounding and vice versa in order to keep the temperature of the system constant. Adiabatic process. When a process is carried out in such a manner that no heat is can flow from the system to the surrounding or vice versa, if the system is completely isolated from the surrounding, is called an adiabatic process. Third is isochronic process. A process during which the whole system is kept constant. Isobaric process if it is a process during which the pressure of the system is kept constant. Graphical representation of the four basic thermodynamic processes are shown in left side. It is reversible process. The various types of process mentioned above will carried out reversibly or irreversibly. These terms may be understood as follows. In order to understand a reversible process, imagine a gas confined with a cylinder provided with the frictionless piston under which is filled some very fine sand. Suppose the pressure exerted by the gas on the piston is equal to the combined pressure exerted by the weight of the piston, the pile of the sand, and the atmospheric pressure. Thus, under these conditions, the piston does not move at all, and the state of equilibrium is said to exist. Now, if can one particle of the sand is removed, and the gas will expand every slightly, but the equilibrium will be restored almost immediately. Such a change in called and intensely change. If a particle sand is replaced by change, gas will return to its original volume by the continued removal of the particle of sand. The gas can be allowed to undergo a finite expansion, but each step in the expansion is an infinitesimal one and can be reversed by an infinitesimal change in the external condition. At all times, the equilibrium is restored immediately. Thus, the necessary condition for the reversible compression is P external is equal to P internal plus dP, and the reversible expansion is P external is equal to P internal minus dP. In general, we can write reversible V external is equal to P internal plus minus dP. Irreversible process which is carried by out infinitesimally slowly, so all changes occurring in the direct process can be exactly reversed and the system remains almost in a state of equilibrium with the surrounding at every stage of the process. On the other hand, a process which can does not meet the above requirement is an irreversible process. In other words, an irreversible process is defined as the process which is not carried out infinitely slow. Instead, it is carried out rapidly so that the successive steps of the direct process cannot be retracted and any change in directional state disturbs the equilibrium. The main point of the difference between irreversible and irreversible process may be summed up follows. Reversible process. The process is carried out intentionally slowly. Difference between the driving force and the opposing force is very small. Irreversible the process is not carried out by infinitely slowly but is carried out rapidly. The difference between the driving force and the opposing force is quite large. In reversible process, any stage during the process equilibrium is not disturbed. In irreversible equilibrium may exist and completion of the process. Reversible process it take place in finite times of completion. Reversible process a infinite time of completion. Reversible process is only imaginary and cannot be achieved in actual practice. Irreversible processes actually occur in nature. Irreversible process work obtained in the process is maximum, and irreversible process is not the maximum. Like this, some thermodynamic quantities, a number of the thermodynamic quantities appear during the study of the thermodynamics: internal energy, heat, okay, enthalpy, entropy, free energy, and the free terms are briefly discussed. Internal energy, it is already been mentioned that whenever some energy process, physical and chemical occur, it is combined when some energy may appear in different forms such as light, heat, and work. The evolution of the absorption of energy in different processes clearly show that the every substance or the system containing one or more substances must be assisted with some definite amount of energy. The actual value of the depends upon the nature of the substance and the condition of the temperature, pressure, volume, and composition of the system. Different types of energy is associated with atoms and molecules, such as electronic energy, nuclear energy, and chemical bond energy, and potential energy, and the kinetic energy, which is further the sum of the transitional energy, vibrational energy, and rotational energy, is usually represented by the U and E. U or E is equal to UdU plus E and EC plus EP plus EK. The energy the stored which is substance system is called the internal energy. No doubt that every substance or system is a definite amount of an internal energy, but it is not possible to find the absolute value because it involves certain quantities which cannot be measured. However, fortunately, it is required to know the absolute value of the internal energy possessed by any substance which is required to in different processes is simply the change of internal energy when the reactant changes into products or when a system changes from initial state to the final state. This is easily measurable and it is represented by Vu and V del E. Internal energy change in if the internal energy of the system is initial state is U1 and the final state is U2, and the change of the internal energy is del U. Del U is equal to del U2 minus U1. Similarly, in a chemical reaction, UR is the internal energy in the reaction, UP is the internal energy of the product. The energy accompanying the reaction would be del V. U is equal to del P minus UR. Internal energy of the system changes the heat possessed in a or out of system. Work is done or by the system matter internal use of the system. Internal energy as a state function. Internal energy is a state of a function depends upon on the state of the system and the independent of a method by which this state has been attained. For example, 1 mole of the CO2 at 300 Kelvin and 1 atmospheric pressure will always have the same internal energy respective. In fact, throughout this condition from 500 Kelvin and 5 atmospheric pressure from 1000 K and 10 atmospheric pressure. The internal energy is state function may be further explained as follows. Consider a system containing amount of water, thermos, flask, insulated water. Let us change the internal energy of the system doing work, adiabatic work. This can be done in the following two ways: by doing mechanical work by rotating a smart of pedals, by adding doing electrical work with the help of an immersion rod. In each case, temperature is found to rise by the same value, say from T1 to T2, the same amount of work done, respective of the fact how it is done, produces some changes in state measured in the term of temperature change. Hence, we write del U is equal to del U2 minus U1. Sign of del U is obviously from the equation. Two important points about internal energy. The internal energy depends upon the quantity of the substance containing in the system. Hence, it is an extensive property. The internal energy of ideal gases is in function of temperature only. Hence, it is isothermal process. B is work. As learned from lesson in physics, work is said to be whenever the point of the application of force is displaced in the direction of the force, and F is magnitude of the force, and del dl is the time displacement of the point and application of the direction in force act, and the work is given by W is equal to F into dl. Work done is equal to a generated force into a generalized displacement. First is electrical work. The generalized force is EMF, and generalized displacement is the quantity of the electric energy flow through the circuit. Hence, electrical work done is EMF into quantity of the electrical. Second is the work of expansion, compression, or pressure volume work. These types of work is involved in the system containing of gases. This fact most important form of work used in the study of thermodynamics. It is the work done when the gas expands through contrast against the external pressure. Expansion work is follows. Consider gas involved in the gas cylinder fitted with frictionless piston. Suppose area of the section of cylinder is a square centimeter. Pressure of the piston is P, which is slightly less than the internal pressure of the gas, so gas can expand. Distance through the which can expand dl centimeter. We found the formula of W is P integration of V1 to V2 del dV is equal to P into V2 minus V1 is equal to P del V. This is the formula of the work done. Units of W. The unit of work as same of the energy, ergs or joules. Work done in isothermal reversible expansion of a ideal gas. The small amount of work done of a sand gas expanded through a small volume dV against the internal pressure P exists external is given by the difference in the work done is reversible expansion or reversible expansion. In the reversible expansion of a gas, the internal pressure is only infinitely less than the internal pressure at each stage. Hence, the expression for the work done can be taken as by the following equation. In the reversible expansion, internal pressure is much different from the external pressure. For example, the internal pressure is much higher than the external pressure. As the expansion takes place against the external pressure reversibly, the work done will be given by W is equal to minus P external into del V. For the assumption in volume, the work done is isothermally and reversibly. For the work done, the area under the isotherm AB area is AB. V1 and V2 represent the work done reversibly. The under area isotherm BC B1, V1 and V2 represent the work done irreversibly. Note that in the reversible expansion, external pressure remains constant, but in reversible expansion, external pressure has been decreased continuously, so the remains infinitesimally smaller than the internal pressure. Why a smooth curve of the type AB is obtained by the isothermal reversible expansion. Suppose the external pressure is not constant and it is changed in number of finite steps. Work done is small games summoned over the step will be. This represents irreversible expansion. Reversible work of expansion is maximum work. For reversible expansion, P external should be intensely smaller than the P internal. In other words, P external is maximum possible value of pressure because the pressure is greater than the value of the expansion can occur. Similarly, explain the reversible work of compression is in the minimum work. Free expansion for an ideal gas expansion against vacuum. Points of difference between the reversible and irreversible processes. Reversible process is a process in which any stage reaction can be reversed by reversing the condition of the temperature, pressure, and extra by small amounts. In this process, the driving force is infinitesimally greater than the opposing force of all types. It is carried out infinitesimally slowly at this stage. During the process, equilibrium remains undisturbed. The concept of the reversible process is only imaginary. It cannot take place in the actual practice. Work done during reversible expansion of a gas is maximum work. Reversible process it is a process in which any stage of the reaction cannot be exactly reversed by the reversing condition or temperature, pressure, etc. In this process, driving force is much greater than the opposing force. It can take place rapidly. Equilibrium is disturbed at which stage of the process. All naturally occurring processes are reversible. Work obtained during a reversible expansion is less than the minimum work. Says heat just as work is a form of energy which exchange between the system and the surrounding. As a result, expansion of contraction of a gas because of the difference in the internal pressure of the gas and external pressure. Similarly, heat is another mode of the energy exchange between the system and the surrounding. As there is a difference of temperature between them, it is usually represented by the letter Q. Heat sign convention of the Q when heat is given by the system is negative and absorbed by the system is called and the sign is positive. Units of Q is calories, joules. 1 calorie is equal to 4.184 joules and 1 joule is equal to 0.2390 calories. Work and heat are not state functions. Unlike internal energy, the work done usually a process does not depend upon merely on the initial and the final state of the function. It depends upon the path followed. Hence, the work is not a state function but a path function. This may be made clear as follows. Suppose we wish to change the system of A to B. This may be done by the following different paths as shows. Confining overall the work of estimation only in which work done over a small change in volume dV and P dV, where P is external pressure, then the total work done is some P dV terms into that is equivalent to the area under the curve PV diagram. You have to see in the right side different path following the going A to B state. And the formula is del U is equal to Q plus W, or Q is equal to del U minus W. Del U is a state function, but W is not a state function, hence Q is not a state function. First law of thermodynamics. The first law of thermodynamics is simply the law of conversion of energy, which states that the energy cannot be created nor be destroyed although it may be converted one form to another, or the total energy of the universe if the system and the surrounding remains constant, although it may be undergo transformation from one form to the another, or the energy of an isolated system is constant. Justification of the first law of the thermodynamics is this law is purely a result of experience, that is no theoretical proof for it. However, some of the following observations support the validity of this law. Whenever a certain quantity of the sum from the energy dispersed and exactly equivalent amount of some other form of energy and must be produced. For example, in an operation of electrical fan, the electrical energy is consumed is converted into the mechanical work which moves the blades. The electrical energy supplied to a heater is converted into heat, whereas electrical energy passing through the filament of a bulb is converted into light. Since water can be decomposed by electrical current and to gaseous hydrogen and oxygen, it is found that the 285.8 kilojoule of electrical energy is used to decompose 1 mole of water. The reaction H2O is plus 285.8 kilojoule is after reaction H2 gas plus half O2 gas. This energy must have been stored in hydrogen oxygen, since some amount of energy in the form of heat is released when 1 mole of the water is obtained from the gases hydrogen and oxygen. H2 plus half O2, that after reaction H2O plus 285.8 kilojoule heat energy. Thus 285.8 kilojoule of electric energy which is supplied to the system substance after observation has been recovered as later as heat energy. Electrical energy supplied is equal to heat energy produced. This energy is converted in the form of to although one form of energy can change into the other form. It is impossible to condense a perceptual amount of mechanical zooming energy. There is exact equivalence between heat and mechanical work. For every 4.814 joules of the work done, a calorie of heat produced, and vice versa. Mechanical formulation of the first law of thermodynamics. Relationship between internal energy work and heat. The internal energy of the system can be increased by two ways: by supplying heat to the system or by doing work of the system. Suppose the initial internal energy of the system is U1, absorbed heat Q, internal energy will become U1 plus Q. For further work is energy will further increase and becomes is equal to U1 plus Q plus U W. Then del U is equal to Q plus W. This is mathematical formation of the first law of thermodynamics. If the work done is expansion and W is equal to minus P del V, then the formula is del U is equal to Q minus P del V. or Q is equal to del U plus P del V. Two interesting results follows are these. You have to see numericals and you can solve these. Problem 1. These are the NCRT formulas. Enthalpy, another useful state function. The term internal energy has already been explained. Another important except definition of the internal energy changes follows from the first law of thermodynamics, according to which del Q is equal to del U plus P del V. In this process of carried out a constant volume, del V is equal to 0. The above equation then reduced to the form del V is equal to del U, where subscribed to V indicates constant volume. Internal energy changes is the heat absorbed or evolved by the constant volume. It may mention further that del U is a state function. Therefore, QV is also a state function. If a process is carried out at constant pressure, as usually the case because most of the reactions are studied in vessels open, the system consists of a gas confined in a cylinder fitted with a piston, and the external pressure acting on the piston is atmospheric pressure. The work of extension is given as W is equal to minus P del V, where P del V is the increase in volume and P is the constant pressure. According to the first law of thermodynamics, we know that Q is equal to del U minus W, where Q is the heat absorbed by the system and del U is the increase in internal energy of the system, and W is the work done by the system. Under condition of the constant pressure, putting W is equal to P del V represent the absorbed QP. QP is equal to del U plus P del V. Del U is equal to U2 minus U1, and del V is equal to V2 minus V1. Then we have to find H is equal to U plus PV. Enthalpy change of system is equal to the heat absorbed or evolved by the system is constant pressure. Del H is equal to del U plus P del V. Enthalpy change is an accompanying a process may be also defined as the sum of the increase in internal energy of the system and the pressure volume work done is the work is expansion. Physical concept of enthalpy or heat constant. In the above discussion, the enthalpy has been defined mathematical expansion. H is equal to U plus PV. This energy may be many kinds. The energy stored within the substance of the system is available for conversion into heat is called the heat constant or enthalpy of substance of the system. We have the main points of internal energy and enthalpy. You have to read these 5 points. Both internal energy and enthalpy are state functions, both extrinsic properties. The absolute value of neither internal energy or enthalpy can be determined. Internal energy changes in heat, evolved constant temperature and volume. In a cyclic process, when the system turns original state after a number of changes, del U is equal to 0. Numerical problems. Relationship between the heat constant pressure at constant volume. Del QP is equal to del H and QV is equal to del U. Del H is equal to del U plus P del V. Del H is equal to del U plus P into V minus 2 minus V1 is equal to del U plus PV2 minus P1 PV1. For ideal gas, PV is equal to nRT, PV1 is equal to N1RT, or PV2 is equal to N2RT. Then we have found del H is equal to del U plus del NGRT, and the QP is equal to QV plus del NGRT. Condition for under QP and is equal to QP or del H is equal to del U. When in reaction is carried out in a closed vessel, the sum volume remains constant. When the reaction involves only solid or liquid or solution or a but gaseous reactant or product, this increased volume changes solid and liquid during a chemical reaction are negligible. When reaction involves gaseous reactants and products but their number of moles are equals, and these are the problems we have to solve these. Heat capacity, specific heat capacity and molar heat capacity. Definition: heat capacity of a system is defined as the amount of heat required to raise temperature of the system through 1 degree Celsius. Formula of the heat capacity is C is equal to Q by T2 minus T1, and Q is equal to Q by del T. Specific heat capacity or specific heat of a substance is defined as the amount of heat required to raise the temperature of 1 gram of the substance through 1 degree Celsius. Molar heat capacity of a substance is defined as the amount of heat required to raise the temperature of 1 mole of substance through 1 degree Celsius. Here's a two example types of heat capacity or molar heat capacity. Since Q is not a state function, depends upon the path followed, therefore C is also a state function, hence to the value of C is conditioned as such constant volume or constant pressure have to be specified which define the path. Thus there are two types of capacity such as the heat capacity at constant volume or heat capacity at constant pressure. The heat is supplied to the system is raised temperature through 1 degree Celsius, keeping the volume of the system constant, and is the heat capacity and constant volume. Similarly, the heat supplied to the system is raised temperature through 1 degree Celsius, keeping the external pressure constant, is called the heat capacity or at constant temperature. Let us see in these the different formulas for the heat heat capacity. Cv is equal to del U by del T for the ideal gases. Heat capacity is constant volume may be defined as the rate of the change of internal energy and the temperature at constant volume. Heat capacity at constant pressure may be defined as the rate of the change of enthalpy with the temperature at constant pressure. The alternatively method for the Cv is equal to n Cv bar or and Cp is equal to n Cp bar. Relationship between Cp and Cv: if the volume of the system is kept constant and the heat is added to the system, then the work is done by the system. Thus, the heat absorbed by the system is used by the complete to increase the internal energy by the system against the pressure. If the system is kept constant and the heat is supplied to the system, then the work done is expansion. Is also work done by the system is addition to the increased internal energy. Thus, if the constant pressure and the temperature of the system is said to be raised through the same value at constant volume, then in some extra heat is required for doing the work of expansion. Cp minus Cv is equal to del H by dt minus du by dt. H is equal to U plus Pv. Pv is equal to RT for 1 mole of ideal gas. H is equal to U plus RT. Then we found the formula of Cp minus Cv is equal to R for 1 mole of the ideal gas, and the Cp minus Cv is equal to Nr for the number of gases. Exothermic reaction: the reaction in which heat is absorbed are called the exothermic reactions. Also, the heat is absorbed can be written as the plus sign, through which reaction is usually products, and the minus. For a few examples of exothermic processes are these: N2 plus O2 is equal to 2NO minus 180.07. In these reactions, minus heat is absorbed. Exothermic and endothermic reaction: in terms of del H, the enthalpy changes del H accompanying by the reaction is given. Del H is heat constant for products minus heat constant of reactants, Hp minus Hr. Reaction is exothermic heat is required to out a reaction if the total heat is constant. Heat is more than the products, but it accordingly above equation del H is negative for exothermic reactions, positive for endothermic reactions. The branch of chemistry which deal with the heat changes accompanying chemical reaction is called electrochemistry. You have to see in the left side figure 6.1. For the first is exothermic reaction and second is endothermic reactions. Thermochemical reactions: when a balanced chemical equation not only indicates the quantities of different reactants and products but also indicate the amount of heat involved or absorbed, as in the above reaction, is called the thermochemical reaction. However, constancy of the usual practice about the balanced equation functional coefficient may be used in writing a thermochemical equation. For example, the formation water is H2 plus half O2 is equal to H2O plus 285.85 kilojoule per mole, and thus 285.2 kilojoule is produced when 1 mole of hydrogen reacts with 0.5 mole of the oxygen. Some convention about thermochemical equations are for exothermic reaction. Del H is negative, whereas endothermic del H is positive unless the otherwise mentioned. Del H values are the standard state of the substance to 98 Kelvin and the 1 bar pressure. The coefficient of different substances represent the number of moles reacted and formed by the heat changes represented in the equation. These following physical state, the different substances may be mentioned as the heat evolved or absorbed depends upon the chemical state. Reaction is reversed. The sign of del H changes but the magnitude remains the same. Here the reaction or enthalpy of reaction or enthalpy change of reaction, the amount of heat evolved or absorbed in a chemical reaction when the number of moles of the reactant or represented by the chemical reaction have completely reacted is called the heat of reaction or enthalpy of reaction or enthalpy change of the reaction, and it is represented by the del RH. We have to see the some example for these factors on which the heat of reaction depends. The heat of reaction depends upon the number of the factors explained. Is quantity of the reaction involved and physical state of the reactants, entropic modification for this concentration of the solution, temperature, condition for the constant pressure and volumes. Standard enthalpy of reaction. The enthalpy change in the reaction depends upon the condition under the reaction is carried out and initially specify some standard condition. The standard enthalpy of a reaction is enthalpy change accompanying the reaction when the reactants and products are taken in the standard state. Different types of heat and enthalpy of reactions. Heat of reaction or enthalpy is generally from used heat energy. The listed fuse heat of a reaction is enthalpy of combustion. The enthalpy of combustion is a substance defined as the heat change. Usually, the heat evolved when 1 mole of substance is completely burnt or oxidized in oxygen. Standard enthalpy of combustion if the amount of heat evolved when 1 mole of substance under standard condition 298 Kelvin 1 bar pressure is completely burned to form the products. Also under standard conditions it is represented by the del C H. Calorific value for food and fuels just molecules. Kerosene oil, diesel oil are combustion of food. The calorific value of the fuel or fuel is amount of the heat is calories or joule produced from the complete combustion of 1 gram of the fuel of the food. You have to see calorific value of some common fuels and fuels. Charcoal is 33, wood is 17, drug cake is 6 to 8, kerosene oil is 48, and food for butter is 30.4, ghee is 37.6, milk is 3.2. Second is enthalpy of formation. The enthalpy of formation is substance is defined as the heat changes, the heat evolved or heat absorbed. Even more, the substance is formed from the elements under given conditions of temperature and pressure. It is usually determined by that F. Some important points you have to read these. Third is enthalpy of neutralization is an acid base is defined as the heat change. Usually the heat is 1 gram equivalent of the acid is neutralized by base reaction during the carried out in the dilute aqueous solution. Fourth is enthalpy of solution of substance is particularly a solvent is defined as the enthalpy changes amount of energy required when more of substance is dissolved in a specified amount of the solvent. However, if change in volume of the solvent, further addition of the solvent under does not produce any more heat, it is called enthalpy of solution or infinite solution. Fifth is enthalpy of atomization when 1 mole of the given substance dissolves into gaseous state and the enthalpy changes accompanying the process is called enthalpy atomization. Sixth is enthalpy of ionization when mole of the covalent compound and dissolution in water split or produce ions in the solution. Enthalpy changes accompanying the process called enthalpy of ionization. Seventh is enthalpy of formation of ion when an ionic solid is dissolved in water. The ions are produced in the aqueous solution. For the reaction formation of ion is aqueous solution. Enthalpy of formation del H positive ions are aqueous solution is that taken as 0. Here is enthalpy of hydration. The enthalpy of hydration enthalpy changes heat evolved or absorbed when 1 mole of the anhydrous salt combines with the required number of the moles HNC into the hydrated salt is called enthalpy of hydration or heat of hydration. So ninth is enthalpy of hydrogenation. The amount of enthalpy change in take place one mole of the unsaturated organic compound is completely designated is called the enthalpy of hydrogen. And enthalpy of entropic transformation. The enthalpy change in takes place from one mole of the form of entropic modification to another is called enthalpy of entropic transformation. Thank you.